Hello and welcome back to AP Pre-Calculus. This is lesson 2.13, part 1, Exponential and Logarithmic Equations. All right, a quick overview of our properties of exponents. Remember, when we multiply like bases, we add exponents. When we raise exponents to new exponents, as long as there's not a plus sign or a minus sign in this parenthesis, we multiply those two exponents together. A negative exponent puts you in the other side of the fraction. So if it's in the numerator, it goes down to the denominator, right? Logarithms, remember logarithms are another way to show an exponent. So when I multiply, it makes sense that this is an addition because we add exponents when we multiply. When we divide, see a division right there? We have a negative exponent. Whatever's in the bottom will be negative, so the logarithm will be negative, all right? And then the power property, this is the big one. When you have a logarithm raised to a power, you can put that power out in front and multiply the exponents together. All right? Converting, we're going to have to be good at converting, right? Rewriting exponent world into log world and log world into exponent world. All right? Hopefully we've practiced that enough and you're good at it because we're going to use it a lot here. So right now, we're just going to be dealing with equations that have only one log or one exponential function. And that just means, exponential function means that you have a base where the variable is up in the exponent, okay? So here are the steps that we have to follow. First, we're going to isolate whatever term has the log or whatever term has the variable in the exponent. Isolate it on one side, move everything else to the other side. Then we are going to write the equation to the alternate form. So if what I have is an exponent, I want to rewrite it as a log. If it's a logarithm, I want to rewrite it as an exponent, all right? Then we're going to solve for the variable if necessary, and then simplify or round the answer. So if it's a fraction, simplify it. If it's a decimal, round it to 4 decimal places. All right, let's look at example 1a. So I have 4 to the x minus 2 equals 7. So that is an exponential problem. So I'm going to isolate the term that has the exponent, the variable exponent. So 4 to the x equals 9. And now I want to rewrite this in the other form. It's in exponent form, so I want to write it in logarithmic form. So remember, logarithms are equal to exponents. So I fill in the exponent first. Which of those 4 things is the exponent? Well, obviously, it's the x. All right? Then I want to put the base down there below the log. Which is those is the base? Well, 4 is the base. I only have one thing left. I have a 9. There we go. And since they said leave it in exact form, this would be my answer, okay? Let's look at B. Again, it's an exponent problem, so I need to get this 2 to the x plus 3 by itself. So I'm going to subtract. I get 21. So now I'm going to write it in log form. Logs are equal to exponents, so it's equal to x plus 3. Which of those is my base? Well, that's the 2. And then what's left over is 21. So now we have to solve for x, right? So I'm going to put the x on this side, and I'm going to write it maybe a little bit weird for you guys. So the reason I put the negative 3 in front is because sometimes when you write it like this, log of 21 minus 3, we're not sure if those are supposed to go together or not, so you'd have to put parentheses. So, I mean, I could have wrote it like that, and it would have been okay, but you don't want to just leave it 21 minus 3 without putting parentheses there. If you put the negative 3 first, you don't have to worry about that parenthesis. But parentheses are always a good thing to add. So if you wanted to put it in there, you could do that also. All right, let's move on to C. I have another exponential problem. I'm actually going to move the negative 4e to the x over to the other side because I want it positive. You don't have to do it this way, but I like that stuff to be positive, which means I'm going to have to add the 7 to this side, right? So plus 7, I get 10. And then I'm going to divide by 4. So I got e to the x equals, and we can leave it 2.5 if we want to. That's fine. All right, so example 2, we have logarithmic equations. So we want to isolate the log. And by isolate the log, I mean log and then the thing that comes after it. Usually it will be in parentheses. So everything that's after the log in parentheses stays, everything else got to go. So if we look at A, that 4 and that 2, they've got to go, right? So hopefully you guys don't have to see me subtract 4 and divide by 2. You can do that hopefully in your head. So we get there. And so now we want to write it in the other form, okay? So this time I want to take my base and I want to raise it to the exponent. Remember, logarithms are equal to exponents. So this 3 right here is the exponent. And we put the parentheses on the other side, okay? And now we can just solve that. That's 27. I subtract the 3, and I get 24. Nice and easy. Look at B. Everything in the parentheses after the log stays, and everything else got to go, so the 2's got to go. So I got log base 5, 2x minus 1 equals 2. The base is 5. Logarithms are equal to exponents, so that's the exponent. Goes up there. Parenthesis goes on the other side. And then we solve. So I got 25 equals 2x minus 1. Hopefully you can do that two-step in your head. So add 1 is 26, divide by 2 is 13, and there we go. And then last but not least, that 5 in the denominator got to go. So I have ln of 2 minus x equals 5. The base of natural log is e. Logarithms are equal to exponents, so that's the exponent. 2 minus x. Now we get x by itself. I'm going to move the x to the left-hand side so it becomes positive, which means I'm going to move that to the right-hand side. It becomes negative, so 2 minus e to the 5th. And we leave it like that because we want exact form. So now we're going to start working with equations with multiple logarithms, which makes it a little bit more complicated. I wouldn't say that it's all that much harder, but it is a little bit more complex. You're going to look at your equation and you're going to notice that, hey, there's more than one log. So when we do this, what I would like you to start out doing is to look at all of your terms. Remember, terms are separated by plus signs and minus signs. So look at every term. If you want to count them up, that's great. But I want you to try and notice if every term has a log or if there are some terms that don't have a log, like if they're just a regular number, okay? So if you have a whole bunch of terms and at least one of them doesn't have a log, you're going to do form 1, right? You're going to get it to where we get one logarithm on the left and a number on the right. If all of your terms have a logarithm, then you're going to set it up in form 2. You're going to condense all the logs on the left, you're going to condense all the logs on the right, and it's going to look like form 2. If we end up in form 1, well, we just did problems like in form 1, so that's going to be pretty simple. If we get into form 2, then really that's the easiest way, because if I have log base 7 of x equals log base 7 of 5, I know that x has to be 5 because the logs and the bases are the same. The only thing that has to be equal is the stuff that comes after the log, right? So it's going to look like we're just crossing out the logs and the bases. We're not doing any math there. We just don't really care about them, okay? Because they're already equal. We need the rest of it to be equal. Hopefully that makes sense. Either form we got to make sure that we check for extraneous solutions. We didn't really talk about it in example 2, even though we probably should have. Whenever you have an x after a logarithm, we have possible domain issues. Remember, you can't have a 0 or negative. It's got to be a positive number after the logarithm. So we got to make sure that the answer that we got out doesn't cause that parenthesis after the log to be negative or 0, okay? Remember, we call those extraneous solutions. And look at important note number 2. You can't just, like, we're going to get so used to form 2 where we just cross out the logs, we end up getting a little crazy. Look at note 2. It said log x plus log y equals log z. We can't just cross out all 3 logs. You can only cross out one log on the left and one log on the right. And you're not really crossing them out. We're not doing a math thing. We're setting the left side equal to the right side. And since the log and the base are the same on both sides, we don't care about them anymore. but we have to use our properties of logarithms to get it down to where we have one log on the left and one log on the right. We can't just cancel out a whole bunch of logs. All right, let's do example 3. Hopefully that will make sense when we do an example. All right, so let's see here. On A, let's count up how many terms we have. This is one term, this is one, and this is one. All right, so I have 3 terms. All 3 of them have logarithms. So that's going to be form 2. All right, I want to get it down to one log on the left and one log on the right. Well, on the left, I have 2 logs. So how can I condense those 2 guys right there? Well, it's a multiplying idea, right? So that's what I could do. Now look, this log and its base of 10 and this log and its base of 10 are already equal. So I don't have to worry about those. But this 3 times x plus 4 has got to be equal to 5x minus 2, right? So we solve that. 3x plus 12 equals 5x minus 2. I'm going to move the 3x over to the right. That makes 2x. I'll move the negative 2 over there. It makes 14. So x equals 7. Don't just go circle 7 because you think it's the right answer. Like, our work is good, but it might be an extraneous solution. It might have already been told, hey, you can't be part of our domain because you're going to mess up one of the logs. So we have to go back to the original equation and put 7 in where we see x. Okay, that's 7 plus 4 is 11. I can have an 11 in there. 5 times 35. Yeah, okay. So there are positives everywhere. So I'm happy with this answer. Okay. Let's look at B. I have too many natural logs on the left-hand side. Notice I should have counted up all the terms. There's 3 of them. They all have a natural log. So I have to condense. And I saw a minus sign, so I'm going to do that. So x plus 1 goes on top. 3x minus 5 goes in the bottom. And the ln of 7 goes over here. Natural logs on both sides, they're already equal. So I'm only worried about this guy. That's what has to be equal. I can't have an x on the bottom. There's certain places that x cannot be and us solve, and denominators are one of them. So I have to get it out of the denominator. So I'm going to take this whole thing and multiply it over here. So I'm going to get x plus 1, and I'm going to get 3x minus 5 times that 7. We'll clean that up a little bit. What's that, 21x minus 35? I'm going to subtract the x to the 21, so that's 20x. I'm going to add the 35, so that's 36. And then I'm going to divide. When I simplify it, we get 9/5. I guess if you wanted to, you could put 1.8. I think that would be okay. So now we got to check our answer and to make sure it's not extraneous. So remember, the parentheses need to be positive. So if I take 1.8 and I put it right here, will it be positive? Yes. If I put it right here, what am I going to get? Well, 3 times 1.8 is, I think, 5.4. So 5.4 minus 5 is still positive, and then the 7 doesn't even have an x. So this answer is also fine. It's not extraneous. And again, since we didn't have to round our decimal, I think 1.8 would be just fine. All right, why don't you pause the video and give C and D a shot. All right, hopefully this is where you got to. So I got 2 answers, 2 possible answers. So let's go ahead and check our answers just to see if the parentheses will be positive. So when I put 5 here, I make 7, that's cool. I make 2 here, that's cool, and that's already 14. 5 is a good answer. Negative 4. If I put negative 4 here, I can stop because that's going to make a negative. Negative 4 it's not wrong. It's just an extraneous solution. It was not part of our domain to begin with because we have some issues with some of our domain numbers. All right, let's look at D. All right, hopefully this is what you did. Remember, natural log has a base of e. This one had 3 terms, but not all 3 terms had a log. So this would be form 1. So we condensed the left side down, and then we rewrote it in exponent form. So we just had to put 3e squared back here, and it's going to be positive because 3e squared is a positive number. So this is your answer. All right, pause again, and let's see if you can get A and B on this one. All right, we had to condense the left-hand side down since there was a minus sign. I know I had something in the denominator. I also had a number in front of the log, which means it went up to the exponent there. And then I had form 2. I don't have to worry about the log base 4s. They're already equal, so I set the parentheses equal to each other. I distributed the 8, moved the x over, and divided, and I got -8. But I have a problem with -8 because if I put -8 in there, it becomes a negative. So this is an extraneous solution, and our answer is no solution. Now, I always get kids mad to go, we did all that for no solution. No, we did all that to get the correct answer. The correct answer is there is no solution to this problem. All right, let's give B a try. Okay, first thing I did is I noticed that not all of my terms had a log. So I need to get all the logs together on one side. So I moved the log of x minus 7 to the left, and at the same time, I moved the -2 to the right. And then I condensed it. I see a negative, that means I'm going to have a fraction, so we have that. And then I rewrote it in exponent form. The base was 10, because I didn't see it, that's common log. Logarithms are equal to exponents, so that guy is the exponent, and it was equal to the parentheses. So now if I back substitute this guy into my x's, they both make positive numbers, so this is a correct answer. Now, just to let you know, we could have changed this into a log. Remember, that could be an exponent. So what would my number have to be for the log base 10 of something to be a 2? We could have turned that into a log of 100 and condensed and done it the way we did it on A. So you have options there. That's the cool thing about math is we can write things in a lot of different ways, and we have different ways to get to the answer. In memory of Mr. Flick, who has moved to a different county, there are many ways to Tampa. All right, now we have something that you've probably never seen before. It will look familiar once we get it set up, but in this form, it's weird. It says, let f of x equal the natural log of x plus 15 minus the natural log of x, and let g of x equal the natural log of x plus 3. Find all values of x where the graphs of f and g intersect. Meaning, we're just trying to see where f of x equals g of x, right? So let's write out f of x. ln of x plus 15 minus ln of x equals ln of x plus 3. So now we're right back to what we did a second ago. All right, so we're going to condense this left-hand side to one natural log. I see a minus sign, so I'm going to put a division bar there, put the x on the bottom, put the x plus 15 on the top, and this guy over here. So now I just have to do x plus 15 over x equals x plus 3. Distribute over here, so I got x plus 15 equals x squared plus 3x. So we got a quadratic here, so we're going to move everything to one side. So I got 0 on this side. I got x squared. Move the x over by subtracting, so I got 2x left. Subtract the 15. And now we should be able to factor that. If we can't factor it, we could always do the quadratic formula. If you want to be crazy, you could complete the square, I guess. But this factors with x plus 5 and x minus 3. So we get possible answers of -5 and +3. But we got to check them, right? So take your -5. -5 is good in this one. It makes positive. But it is not good in this one. As soon as one of them is negative, That is an extraneous solution. Let's see if our answer is going to be the one we always loved, no solution. So let's take our 3. I put it here, 3 plus 15, that's positive. That's positive. 3 plus 3 is positive. 3 is good. All right? All right, let's do that again. Go ahead and pause the video, give this one a shot, and start it back up when you're ready. Okay, look through this and let's see if you got pretty close to the same thing. Hopefully you did get the same thing. Just real quick, I've been being really lazy about writing it like this. Let's make sure that we're writing our x equals on this because, again, we're in a high-level math class. They're going to be a little bit more picky on things. You're getting college credit if you pass that test. So they're gonna look for us to be a little bit better math students than be a little bit less lazy. So I am sorry that I have been doing that, but from here on out, let's make sure that we're trying to always do things right, okay? So we got our 2 answers here. We got 7/2 and -2. So let's go ahead and check our answers up here. So 7/2, that's 3.5. So if I put 3.5 here, I get positive, positive, positive. So that one is good. What I don't want you guys to get in the habit of is seeing that, oh, x is a negative, so that one's going to be the extraneous solution. That is not always the case. So it's always better to go check your answer to see what happens. I put -2 here, I'm going to get -7. This one is no good. And I know that, again, it was a negative in Mr. Francis, but always check. Don't just assume the -1 is going to be the extraneous solution. Okay, so we're going to end this lesson with equations with multiple exponential functions. When we have more than one exponential function, sometimes we can get lucky and we can solve the equation by finding common bases and then using the properties of exponents. So let's look at example 7. A is pretty straightforward. Remember, these are equal to each other, right? Well, the bases are already equal to each other, so the only thing I'm worried about is the exponents being equal to each other. It's not like I did a math operation to get rid of the 2, the bases of 2. It's just they're already equal, so we don't really care about those. We need to make the exponents equal. So once it's like this, it's pretty straightforward. I'm going to subtract 2x. I'm going to add the 1. I'm going to divide by 3. And we don't have any restrictions on our domain in exponential, so we don't have to check anything. We just got to make sure we do the math right, and we get that. All right, let's look at B. I have 8 to the 3x minus 2 is equal to 2 to the x plus 5. Well, the bases aren't the same, so I can't just set my exponents equal to each other. So I'm going to try and get the bases to this same number. Remember, we should never make a base bigger, but we can always make a base smaller if possible. So 8, can I write that in base 2? Well, yes. 2 to the 3rd is really 8, and then I have 3x minus 2 out there, and I have the x plus 5. Now, we do have to do a little bit of work because when you raise a base and an exponent to another exponent, we should be multiplying those together. So that becomes 9x minus 6. And then we can disregard the bases. I'm going to subtract x to the left. I'm going to add 6 to the right, and then divide. I get 11 over 8. X equals 11 over 8. All right, look at C. Well, I got a base 9 and a base 27. So the first thing I'm going to ask myself is, can I turn that 27 into a 9? 9 to the first is 9, 9 to the second is 81. I can't make 27 with base 9. So let's go down to another base. I recognize 9 as 3 squared. And then hopefully you recognize 27 as 3 cubed. And then we just do the same thing. Distribute, I get 4x on this side, 3x plus 6 on this side, subtract 3x, and I get x equals 6. All right, so this one is a little bit weird. I see a fraction. I don't really want to deal with a fraction, but all a fraction is, especially when there's a 1 on top, is I could rewrite that as base 2. What kind of exponent would put 2 in the denominator? Well, that would be -1. and the other side's a 4. I know a 4 is really 2 to the second, and now it's just like the other ones, right? I can distribute that. I get negative 5x minus 7 equals 2x. Move the 5x over. I get 7x, and I end up getting x equals negative 1. Don't worry about it being a negative because we can have negatives in exponents. Remember, we don't have any domain restrictions. And there's my answer. And that concludes today's lesson.